let's apply this idea that a magnetic field can apply a force on a section of wire with an electric current to something that's a little interesting, where we don't just have a wire, we have a loop of wire with current flowing around and back out. We have a magnetic field here, V, and I've drawn out two field lines, but in fact, these are just illustrative. The magnetic field is constant all across this area. I've also noted that the length here on this side is A and the length on the other side is B. With that established, let's take a look at what the force is going to be. So let's start with this section of wire with length A. In this case, we have a current that is flowing in this direction, so basically downwards. And we have a magnetic field that's perpendicular to it, flowing from right to left. So in this case, we can look at what the cross product is to give us this force. So we're going to have a cross product from the direction of the current and then to the direction of the magnetic field. And that's going to give us a force that's downwards. So let's turn that into red, and we're going to say, well, this gives us a force downwards. On the other side, we also have a current going along that is now essentially sort of upwards, and then we're going to cross with the magnetic field, and in that case, the force is in fact going to be upwards. Okay, so we know from our discussion before that the force on a section of wire by a magnetic field is F is equal to ILB, where I is the current, B is the magnetic field, and L is the length of the wire. So in our specific example here, we have a force that's I, A, which is that length, B. Now what we realize is, let's assume this is all able, this wire is on a pivot, it's able to rotate. Well, then there's going to be a torque. So that torque is going to be I, AB, B. Okay, so that's our force, and we've got this distance as well, which is our B. So this is going to mean that it's going to rotate, and it's going to rotate counterclockwise. So we imagine that there's going to be a rotation in this direction. Now, what's going to happen next in this motion? So then, once it rotates 90 degrees, that torque is going to become 0. Because at that point, we're going to have an alignment there of the current and the magnetic field. It's no longer going to provide a force. However, there will be some inertia. So inertia will carry it through. Well, let's take a look at what's going on at that point in time. So I've got this prepared, so I'm going to move it up. So this is the same apparatus, but now it is rotated that 90 degrees. So now we see the same set of electric currents in the same magnetic field, but now in this case, we're not going to have that same torque. Instead, what we're going to have is, if we look at this current, and then we look at the magnetic field, and we do the cross product, we're going to have a resulting force that is exactly upwards. And so this arrangement, while producing a force, doesn't provide a useful force because it's just going to leave it where it is. And what we're interested in doing in this system is rotation all the way through. So it's going to have this torque initially, and then it'll lose it once this orientation between the current and the magnetic field becomes such that there's no more torque. So how are we going to solve this if we want it to continue to rotate? Well, inertia will carry it forward. However, then what's going to happen is, if we move a little past that point, then the torque is going to be in the reverse direction. And so that's going to lead it to stop. It may take a few cycles to settle, but it will settle. So what we need here is a way that we can, at that exact moment, we're going to flip the direction of that current. So what we need is what is called a commutator. So we need a way to flip the current direction. To keep motion. And this is a commutator. And so what a commutator is going to look like vaguely is essentially you've got your wire coming in, and it's going to have this ability to connect to a device, a commutator, which is going to be kind of shaped like this, and then like this, the other side. And so this will be the wire as well. Oops. And so the idea here is that these wires are connecting. So these are, two wires. So those are connecting over here. And so what's going on here is we've got some source of current, and that's going to flip because this whole thing is going to rotate. So what we're seeing is we're actually going to have this rotation. Let's do this maybe in gray. So here we're going to have this rotation here, and so we're going to have this motion. Going to try and get this aligned reasonably. And so what's going on here is we have this rotation. And so because of this rotation and this arrangement with a commutator, if we line up this gap just right, once these wires kind of reach this point, and they're moving over here, and then they're going to reach this point, and and at that point the current is going to flip. And once that flips, it's going to be able to then have a torque again, and it will be able to continue to move. And so this is how we design a basic electric motor, where we're using this magnetic field and its ability to apply a force on a current to create rotation, and then we could hook up, any sort of mechanical entity that we want to make use of that rotation motion. On the other hand, this same type of design can be used in the opposite way to generate current, since moving a conductor through a magnetic field can actually generate that current flow. And so we can take some mechanical energy from like a waterfall or some other source that's going to drive the rotation, and this process will work in reverse as well. So this is really very useful. So that's a little introduction into applying this ability for magnetic fields to exert a force on a section of wire and make things like motors.